Well, hi everybody. Welcome to this supplemental video here. A little bit, just pick up a couple high points here in the Lecture 6 PDF. So I'm just going to jump ahead here to the part I wanted to talk about. So the first couple pages we've mostly covered in class already. But this one is interesting, I think. So this one asks the question, what is the height and range of flight for a projectile with speed initially v0 fired at theta above the horizon on the moon? So the gravitational acceleration for the moon is about a sixth of gravity on Earth. And so it's just like the example we already did, except instead of having g, you have g for the moon, right? So that's g over 6. And so if you look at it, you get 6 times the v0 squared sine squared theta over 2g. In other words, it's 6 times the height on Earth. And likewise, the maximum height of the projectile on the moon and the range of the projectile on the moon is exactly 6 times what it would be on Earth. That's the way the math works out. So that's kind of neat. Let's see, here says 1. Let's briefly mention that one. Then example 5. Let's see here. This one's a little more substantial. So here, the claim is that we're asked to show that the speed at which the ball, so you got Mr. Top Hat up here, and it shoots a ball off the top of the building, height h, all right, and some speed v0, and then the question says that allegedly the speed at which the ball hits the ground is independent of theta for a fixed choice of initial speed, all right, and so let's see here, we're assuming this is like horizontal ground there. And so I work this problem 2 different ways in Lecture 6, right? So let's track through the first way. The first way, I just, do direct battle with the kinematic equations that involve time just directly, all right? So y1 is the height of the building, y equal to 0 is the ground level, the acceleration is minus g j hat. I'm using j hat rather than y hat because well, anyway. Every so often I'm influenced by the book. So anyway, y of t is y1 plus v0 sine theta t minus 1/2 gt squared. There's your formula for the y as a function of time, right? And we're interested in the time when it hits the ground, which is when y of t is equal to 0. So lo and behold, we've got a quadratic equation in t. And so let's see, then I multiply this equation by well, I divide by g over 2, however you want to look at it anyway. Multiply the equation so that the coefficient of t squared is 1. And then I'm completing the square on this step here. And so once you do that, you can then cipher. Or, if you don't follow this algebra here, this is just the quadratic formula on this quadratic equation. If you want to think of it that way, that's fine. But anyway, there are 2 solutions, plus and minus. v0 sine theta. Let me scooch this up a bit here. Sorry about that. So there are two solutions here, right? Plus or minus square root of v0 squared sine squared theta plus 2y1g here. And so physically, it's pretty obvious we want the plus solution, right? Because we're looking for, you can understand what's the mathematics if you think about the picture, right? The minus solution, the math doesn't know, in some sense, that the projectile started here, right? And so if time goes negative, you just go do back to there, right? So that's the negative solution. It's as if, it just was fired here, it achieved velocity v0, and then it kept going, right? So that's like physically, that's why there's a minus solution there, but we're not interested in that one, right? So we choose the plus solution. That gives us the time to hit the ground up there, and then you have to plug that bad boy into. Let's see here, what do we do? Plug it into the velocity as a function of time equation, which is v0 sine theta minus gt. T just happens to be this mess right here. And yeah, so these 2 terms cancel. And they just leave you with minus v0 squared sine squared theta plus 2y1g. This g and that g, they be canceling. Leave you a minus though, all right? And so that's the y component of the velocity at the time the projectile hits the ground. But we know that the x velocity is constant, and it's v0 cosine theta, so what's the speed? Well, the speed we're in 2 dimensions, right? So it's the square root of the x part plus the y part squared, right? Vxt plus squared plus vyt plus squared. And so that gives you a cosine squared. The other one gives you a sine squared. And look at that. Sine squared plus cosine squared is 1. So the final velocity is in fact independent of theta, which is, I don't know, like at first glance when you see that claim, it's kind of like, really? The final velocity doesn't depend on the choice of theta, whether I shoot the thing straight up, almost straight up in the air and it comes back down, or if I shoot it horizontally and it goes down. Like either way, no matter how you slice it, it has the same speed when it hits the ground for all different choices of theta. I mean, that's a little bit surprising, I think, but there it is. The math. That's what the math says. And so, again, not to kind of an obvious point. Physics is mathematical, right? Okay. Anyway, so here's the same example again, but this time without time. So we've got the timeless equation for the y velocity, vf y squared is v naught y squared minus 2g change in y. Since a j equal to 0, what? Something's lost in translation for me there. Sorry about that, guys. Maybe that's just, goodness gracious, I'm not sure what that is. Let's just, I'm just going to kind of just say, I'm not sure what that is, but let's just ignore that. Sorry about that, guys. If you're ever reading my notes and you have a question about something, don't hesitate to email me. It's all good. Let's see here. So on the other hand, since the x acceleration, the timeless equation for x is kind of boring. It's just vfx squared equals v naught x squared, which is kind of dumb. In other words, the initial and final x velocities are the same. All right, fine. Now the final speed is the x speed. The final speed squared is the x speed squared plus the y speed squared, which is this plus that. All right, and then so v naught x squared plus v naught y squared is v naught squared. And so, yeah, there it is. So, of course, if we don't use time, it's easier. And, well, I'll say more about that later in the course. There's a reason that this is easier, although there's a guiding principle we'll learn later in the course, which will make this way of thinking much more clear. At the moment, it's just kind of a quirky solution. So, whether or not you want to look at the time equations or the timeless equations for a given problem, it kind of depends on what you're after, right? If part of what you're asked involves time, well, then you probably better use the time equations, right? But there are problems where the timeless equation is just the right approach, right? Now this one here is a lot like, I think I put one like this in your mission 2 maybe, right? So if you understand this one, you probably can work that one, or at least at the very minimum I've recommended a problem like this. So here it is. Suppose the speed of a projectile when it reaches its max height is 0.47 times its speed at half the max height. At what angle was the projectile fired? So, all right, so the speed here, right, is, well, the speed is the max height here at v2, right? The speed there is 0.47 times the speed there at v1, right? And so what do we know? Well, we know that the x velocity is the same throughout the flight, right? Because it's projectile motion, and we know that the x velocity is constant. It's v naught cosine theta, right? v2, and we also know that at the top of the flight, at the zenith of the flight, it's completely horizontal, the motion, right? So the y component's 0. So in fact, the speed matches the x velocity there. In other words, v2, which is to say the magnitude of the velocity, the speed here, it's equal to v2x, which is just v naught cosine theta. All right. Now, so let's see here. h1 is half of h2. That's, I'm just labeling h1 and h2 like that. So h2 is the max height. We have a formula for that. Let's see here. So what do I got? What's next up? What's next up here? So the timeless equation for the y velocity applied from event 1 to event 2. An event is a time and a place. I don't think I ever said that in class this semester. My bad. But v2y squared is equal to v1y squared minus 2g, h2 minus h1. So, all right. Now that's 0, and so we can solve for v1y squared, and we get that. And now h2 minus h2 over 2 is just 1/2 of h2, which the 2 cancels, and we just get gh2. All right, so that's g times the max height. But we also have derived in class before that the max height is v naught squared sine squared theta over 2g. So consequently, we've got v1y squared is equal to v naught squared sine squared theta over 2, because of, this is equal to that, which is equal to that, and then the, let's see here, the g's cancel, I think. Sorry guys, I'm trying to track the algebra here for a second. That one is equal to that one, so I plug in this into there. Oh, the g's cancel. When I plug the h2, I'm doing g times h2, so g times h2 is just this divided by 2. Right. And that's equal to v1y squared. Okay, I got it. All right, so then what? Well, then we know that the speed, v2, is 0.47 times the speed, v1, and then I square that, which gives me v2 squared is 0.2209 v1 squared, but v1 squared is v1x squared plus v1y squared, right? Because the speed squared is the sum of the x component and the y component squared. It's added, and that gives me let's see here, what am I doing? Well, that's v naught cosine theta. Let's see here. Where did this 0.7791 come from? What's that? Well, I'm sure this step is just algebra. It's just escaping me as I look at the page right now. Like, you should write down more steps. Yeah, I probably should write down more steps. I was smarter when I wrote these notes. Lay off. Let's see here. Huh. Well, you probably have seen it already. Well, that seems like 1 minus 0.2209. So I must be subtracting. Where's this v naught squared sine squared theta over 2 coming from? Oh, that's the v1y squared, right? So what I'm doing, okay, I see what I'm doing. I was keeping this term on the right-hand side. So this times that is this piece, right? And then I'm subtracting this piece to the other side. And so I also know that v2 is v2x, right? So I think I'm using this equal to that, right? Because v1x is equal to v2x. Okay. And so yes, I'm using that v2 is equal to v2x is equal to v1x. They're all the same, because, well, v2 is at the top of the flight, and the other are x velocities, which are constant throughout the motion. All right. So anyway, once you internalize the things that are true for this problem and do the algebra, we get to that, and then, oh, the v naught squareds cancel. Cool. See, I'm excited about it. Exclamation point. Very good. And that gives me tangent squared theta is, so I divide cosine squared to the other side, and I do the numbers here, 0.7791 divided by 0.2209, which works out to 7.0539 tangent squared, which means then that theta is the inverse tangent of like the square root of this, which is apparently 2.6559, and that works out to 69.37 degrees. So, so this is the general kind of analysis you want to do to solve this kind of problem, something like this. All right. So let's see here. So next up, I had this example 8 to share with you. So this one's a little less fancy. You just have a ball thrown at 7.8 meters per second at 17 degrees below the horizontal. And so here's a kind of picture. So it's thrown below the horizontal like that. And then there's a few different questions. After 4 seconds, it hits the ground. How far from the building does it travel horizontally? And what's the height from which the ball was thrown? And so this is all happening on top of a building, apparently. All right. So from what height was the ball thrown, and then how long does it take for the ball to fall the first 10 meters of its flight? All right, so we'll answer those in order. So let's see here. So we have 7.8 meters per second. It was given. That's 17 degrees. So the x velocity is v naught cosine 17 degrees, which works out to 7.45. And as you can see, the y velocity is negative, and v naught sine 17 degrees. I put a minus out because it's down, right? And so I've got minus 2.2805 meters per second. How far? Oh, I said answering part 2. Part 1 is trivial. We have constant x velocity. So time 4 seconds. So we do constant velocity. Velocity times the time gives me 29.84 meters. That's the horizontal displacement. That's how far it travels horizontally. And we can also calculate the final y, because we also know it takes 4 seconds, right? So v naught y minus gt, which plug in the numbers, you get minus 41.521 meters per second. But once I know that, then I can use the timeless equation to get the height, because vf squared is v naught y squared minus 2g yf minus y naught, which is the height of the building relative to the ground, y naught. So solving for what I'm interested in, the height, I get v naught y squared minus vf y squared divided by 2g, which when you plug in the numbers gives you minus 87.6, but of course that's actually minus the height, right? Because the final is 0 and the initial was where the building was. I mean, I guess I never said where 0 was, right? So in any event, this is minus because it's the final height is lower than the initial height, you know? And obviously the height that we're interested in is 87.6 meters. And then the time for 10 meters to drop, you can just solve the kinematic equation for y for 10 less than the height, right? So 77.6 equals to y of t. That gives you this quadratic equation, and you can solve it like that. I would love to show you. There's a quadratic equation solver in like the, a lot of these basic. You should find your quadratic equation solver in your calculator if you have that kind of calculator, because it's really worth it for physics where you got these ugly numbers. I mean, yeah, you can write down the quadratic formula and plug it in, but by golly, most of you, there's a lot of people who get that wrong when they do it on a test. And if you can find that quadratic solver on the calculator, it's a really good idea for you. I use it a lot of times when I'm like doing things like this, just because I can factor things, but it's so nice to just be able to put in the a, the b, and the c, and like let the calculator apply the quadratic formula to come up with decimal answers, right? Like, that's minus 4.9. G over 2 is 4.9, right? But unfortunately, I'm going to blame my children. I think my children have stolen my calculator at the moment. I can't find it. I will find it. I do have a particular set of skills, although finding calculators is apparently not one of them. We talked about this one in class. I think the picture of it got cut off a little bit in the projector, and you notice that I have now added a vector here. So now I can post it once I find my scan of it. But anyway, I think this was a nice problem. I would hope if I put that problem on a test, like everybody gets it right, you know? Okay, so let's see here. And then finally, just to cap this little supplement off, I want to talk about the asymmetric range problem. Now, I spent about an hour and a half working on this problem today, and I was really tempted to cover it in class, but then I thought about it, and I thought, well, I really shouldn't do that, because this is a hard and interesting problem, but it's not really central to what I'm likely to test on, so it's probably better for me to talk about it here. So those of you who care less can just double speed me and ignore this, right? Whatever. But the problem is this: like, what choice for a given velocity v naught and launching off an initial height, what choice of theta will maximize your range? Now you're like, oh, 45 degrees. We learned 45 degrees. We learned 45 degrees is max range when you're beginning and ending at the same height. So max range 45 degrees is for level ground. When the ground is not level, it's ugly. It's quite ugly. Let's see how. So the range the equation for y is this: my initial height of the building plus v naught sine theta t minus 1/2 gt squared, right? This is projectile motion formula for y, the kinematic equation. And when I solve that for t squared, I get this. Then I complete the square like so. And after completing the square, I take the square root. I get plus or minus. As we were talking about earlier in this video, we choose the plus because of physical reasons. And whoa, yeah, whoa. Look what I'm up against. That's my time, all right, fine. And then I plug that into the delta x equation, which up here, so delta x is going to be the range, right? Delta x is v naught cosine theta t. Well, I figured out what the time was for it to hit 0, so I plug that time in there, and that gives me the range, which I'm calling delta x here. And so the range is that, which I simplify to this. I'm not sure that's really helpful, so I tried that. I'm like, all right, well, it doesn't. Fine, I'm all right, great. So I could continue working on it in the next page. And so, like, I'm just, rewriting the formula, so maybe it's a little bit cleaner, like that. I'm hoping, as I'm doing this calculation, I'm hoping I can find some kind of, like, convenient simplification. But then I said, well, no, let's just put in some numbers and see how it works. So I decided to put v naught equal to 1 meter per second, and I decided to make h nice. And to make h nice, I want that g to cancel. So like I basically did 6 meters divided by 9.8 for my h. And with that, particular choice, that gives me 2hg is equal to 12. And then so like omitting the meters just to reduce clutter a bit, my range is going to be 1 over g cosine theta times big bracket sine theta plus the square root of sine squared theta plus 12, close big bracket. Notice what happens. Like, you can recover the range equation when you put h equal to 0. See that? So if h equals to 0, this just drops down to v naught sine theta, and so then you get 2 of them, and you got the cosine, so you get 2 v naught squared sine theta cosine theta, which then simplifies, of course, to our beloved range equation, which is just what? Like the range equation, remember, for level ground is, v naught squared sine 2 theta over g, right? That's the simple formula. I mean, comparatively simple, which you can easily see 45 degrees gives you that sine theta being 1, which gives you max range, right? This is the uglified version when you're starting from a height and going back to 0, all right? Now, what am I doing here? Well, next up, and I will post a PDF of this for you guys, right? This right here, it just didn't go anywhere. Like, I tried to differentiate it, and I mean, I differentiated, I didn't try, I differentiated it, I set it equal to 0. And I'm just, I'm trying to sort through the derivative and see if I can't see something to help the analysis. And you try some things, and sometimes they work, and sometimes they just kind of go nowhere, and this kind of went nowhere. And I can hide that from you and, pretend like I didn't do this, but I think it's healthy for you to see that this is how we try to maximize something in closed form. At least that's what I do. I differentiate it. I set it equal to 0. I look for a critical number, and if I can find it, great. And if I can't, then I resort to numerical methods. All right, so for me, numerical methods means I start using Wolfram Alpha. So what I did here was I took Wolfram Alpha and I told it, I gave it back my range formula, right, up here, and with the specific numbers put in it, I said maximize this, all right? And so what Wolfram Alpha does is it differentiates, it sets it equal to 0, and it just numerically solves that critical equation. And so what Wolfram Alpha told me was that if I did my original set of numbers, it gave me about 0.27 radians or 15.5 degrees for max range. then I said, oh, well, that's interesting. What happens if I change the height instead of doing 6 meters? So I started with 6 meters over 9.8. That's what gave me the 15.5 degrees. Then I'm like, okay, well, what happens if I do 12 meters over 9.8? Then that gave me 11.29 degrees. Let's see here. Then I made the height a little bit shorter. So this made the height. So I made the height longer. I made the height taller. A lower angle gave me max range. When I made the height smaller than 6, this is half of the height of my original number. That gave me 15.5. Then I got 20.7. If I make the height 1 over 9.8, I end up with a max range from 30 degrees. And if I make the height 0.01 over 9.8, then I'm getting pretty close to 45 degrees. So just to kind of give you a rough analysis of like why that's happening in the formula, essentially if this term 2hg is pretty small relative to this, then this formula basically collapses back to this one, and then the max range is 45. But when this is significant in comparison to that, it drops the angle down lower. And so like the bigger this is, the further it goes away from the 45 degrees maximum range. So yeah, that's it. I'm sure there's a better way to explain that, but that's what I got at the moment. That's the math, and of course I haven't explained this, right? Like to derive these angles through direct calculation, I would have to do some like pretty serious, like I'd have to replace these with their power series or something like that, and look for like solving, like find the best quadratic approximation to this at theta or something like that, and solve that equal to 0 to find an approximate. I mean, it would be quite involved to solve this numerically by hand. And so Wolfram Alpha is extremely helpful for ugly problems like this. And when I say, do something numerically, I'm usually just talking about Wolfram Alpha for you guys. I mean, if you want to use Mathematica directly, you can, but man, Wolfram Alpha is just an overlay of Mathematica anyway, right? And there are other things, but anyway, hey, that's all I got for you guys. I hope that wasn't too boring, and I'll see you Friday.